Welcome to our lecture series on protection technology. These 3 Siemens Power Academy lectures are designed for those who want to expand their knowledge and understanding of relay protection for distribution and transmission grids. Today, we will focus on the physical basics and steady-state conditions of current transformer saturations, mainly for professionals from distribution and transmission grids. We will record the webinar and make the recording and the slides available to all participants. Please type your questions in the Q&A field. We will answer these during the dedicated Q&A session after this series. And now, let me hand over to our expert, Siegfried Lemmer. The stage is yours.
Hello, today's topic is current transformer saturation. This topic is a little bit mysterious thing for many protection people, so it makes sense to have a bit look at it. Don't be afraid, this will not be a deep dive into the theory of current transformer saturation. I picked out a few things which I think are important for protection people to know. So I will talk a little bit about the physical background, what brings us saturation, what is saturation, and then I will talk about what do we have to do in protection to avoid problems with saturation. Not to avoid saturation, that cannot always be avoided, but we have to do correct dimensioning to avoid problems with saturation. So let's start a little bit with the physical basics to understand what happens if we have current transformer saturation. And first, we have to look a little bit at this strange thing, what is a current transformer? Normally, if we talk about a transformer, we talk about a thing where we connect a voltage to one side and then we get a transformed voltage on the other side. That is the use of a transformer in the networks for the power transformer, but also in traditional power supplies. You have a transformer which is used like this. You have a primary voltage and then it's transformed normally down to a secondary voltage with a certain ratio, and the secondary voltage can be calculated like this by multiplying the primary voltage with the winding ratio. The side with the higher number of windings has the higher voltage. Then you can connect a load to this. Then you have some load flow current on the secondary side. And if you reduce this resistor, the current will increase, the power will increase. You can do that until you reach the limits of this transformer. And then you run into an overload situation. And the extreme thing would be if you make a short circuit on the secondary side, that will cause trouble, because then the transformer cannot maintain the voltage, the current becomes too high, the power becomes too high, then it doesn't work. So for a normal transformer, you have to avoid a short circuit on the secondary side. So what is now a current transformer? It's also physically a transformer, but it's used a bit in a different way. What we do there is not applying a voltage on the primary side. In a current transformer, we apply a defined current, and then we get a transformed current on the secondary side, and we must allow the current transformer that this current can flow. So the best thing to do that is to make a short circuit on the secondary side. And there you can already see a big difference. The normal transformer, a voltage transformer, doesn't like a short circuit. For the current transformer, it's the best thing you can do. It likes short circuits. You can also calculate the current on the secondary side. It's the current on the primary side multiplied by the inverse of the winding ratio. So it's exact inverse to the voltage transformer. So that means that the side with the lowest number of windings has the higher current. And also there it's possible, instead of using a short circuit, using a resistor there. For a current transformer, we call this resistor normally a burden. And there the load increases if you increase the resistor. For the voltage transformer, the load would increase if you decrease the resistor. For a current transformer, it's opposite. If you increase the resistor, it becomes more and more difficult for the current transformer to maintain the current, and you can increase this burden up to a certain value, and then you reach the rated power of the current transformer, and then it becomes difficult for the current transformer to maintain the current. And the worst thing you can do with a current transformer is making an open circuit there, because then theoretically you would have extremely high voltage. Practically it doesn't work, but you get problems because you get high voltages there on the terminal. And that is the reason why a current transformer should not be operated with open terminals. A voltage transformer must not be operated with a short circuit. So you see, everything is opposite with a current transformer. This is a model with really an ideal current transformer, which does this transformation from primary to secondary just in an ideal way, taking into account the winding ratio. Unfortunately, world is not that ideal. So in reality, the equivalent circuit for such a transformer looks a bit different. What you see here is a simplified equivalent circuit for a current transformer. It shows only two additional components. That means on the left side, you see the ideal current transformer, which transforms from primary to secondary current in an ideal way. And then on the right part, you see two additional components. The R value, the resistor there, RCT, is the winding resistance of the current transformer. And you have the magnetizing reactance, that is the L0, this reactance. And it's already indicated here in this diagram. This thing is a nonlinear thing, and that is the component which makes us a little bit trouble, as we will see on the next slides. So what do these additional components mean? You see, on the protection device is normally connected on the right side. That means there where we have the burden, this resistor, that is an equivalent for the wiring plus the protection relay. That means the protection relay measures the current there. So now, how do these additional components contribute to the whole topic? The current we want to measure is this one. That is really the transformed current. That is the current we want to measure. The current our protection relay sees is this one. That is the current which flows out of the relay and out of the current transformer and is measured by the relay. And what is the difference? The difference is the current which flows into our magnetizing reactance. That means the more current our magnetizing reactance has, the bigger the difference is between the current we want to measure and the current we really measure. That means we have to look a little bit into this magnetizing reactance if we talk about measurement errors and saturation. An important equation in this context, or an important quantity we need, is the voltage across this magnetizing reactance. And this voltage can easily be calculated by this formula. The voltage is the secondary current multiplied by the winding resistance of the current transformer plus the burden. That means this voltage across the magnetizing reactance becomes the higher the secondary current is, and also the higher the burden is we connect. And before we now go a little bit deeper into this magnetizing reactance story, we have to look a little bit into the standards, because if you see this equivalent circuit, it has a few components, and in reality there are a few more components which makes it a bit more complicated. So you have a lot of different parameters to design a current transformer, a lot of different possibilities. And of course in industry we normally try to standardize things. And for that reason, standards for current transformers have already evolved many decades ago. And first as national standards, that means every country had its own standards. Nowadays, everything goes in direction of IC. So now we have an IC standard, and this standard is the 61869 standard that refers to instrument transformers in general, and it has a part 2, that's why we call it -2, that refers to current transformers. And if you look into this standard, you will see that you first of all have to distinguish between two groups of current transformers. One group are current transformers for measurement. These current transformers are designed for a good measurement from 0 to the rated current plus some overload. And above that, they should go into saturation. And of course, that doesn't make sense for protection. In protection, we want to measure short circuit currents. So these group of current transformers intended for measurement cannot be used. That is one group. We neglect them here. The other group are current transformers for protection. And if you look into that standard, you find a lot of different so-called classes of current transformers. Now you may ask the question, why do we need that many classes of current transformers? Are they all different? The reason behind that is a little bit the development of the standard. So it has normally some history on board. If we look at these classes, we can subdivide this into two groups. Look at the column 2. Question, is there a limit for remanent flux? You see some of them have a yes and some of them have a no. These current transformers with a yes and current transformers with a no, they are really different. A no here means this current transformer has no limit for a remanent flux. A remanent flux means if the current is off, if there is no current in the current transformer, due to the properties of the iron, you have a certain remaining flux there, remanent flux. And a part of the current transformer have no limit for that. We will later on see that can cause some problems. Some of these current transformers, those with the R at the end, PR, PXR, and also TPY and TPZ, they are designed a little bit different. They have a small air gap. That means they have typically a split core with a small air gap, and with that you can reduce the remanent flux. So they are a bit more expensive because you have to split the core, but they have the advantage that they have the remanent flux, that they have a significantly reduced remanent flux. So if we look at those classes where we have no limit for remanent flux, that is the P class, the PX, and the TPX, what is the difference between them? These things are basically, they have no real physical difference. The difference here is only the question which parameters of the current transformers are standardized. The class we will find or the majority of the current transformers we find in our installations are P-class current transformers. That is the upper line. For the P-class current transformers, the standard defines only accuracy limits for symmetrical steady-state conditions. That means if you have a P something current transformers, you can look in the standard, and this current transformers has to meet some accuracy limits, but they are only defined for symmetrical steady-state conditions. If you look, for instance, in the TPX, they have additionally also defined error limits for transient conditions, which is basically better for us because then we know how does the current transformer behave under transient conditions. And in protection, we always have to deal with transient conditions. But these classes were introduced with the standard, but experience shows they are not widely in use. So basically, and that is the reason why all my examples I will show you later on are based on the P-class transformers. You even have the situation, a current transformer can be a TPX current transformer and a P-class current transformer at the same time. They are not physically different. You can take a TPX class current transformer, you just ignore all the definitions for the transients, and then the remaining part are the accuracy limits for the steady-state conditions. So, as I said, in the following examples, I will refer mainly to P-class current transformers. At the end, we will talk about dimensioning rules. If you look into our manuals and want to check the dimensioning rules, there we have different dimensioning rules for all the different classes. That means the chapter about dimensioning rules is rather big because we have to consider all these classes. And additionally, we have to take into account these current transformers tend to become very old. That means if we look into the field, we have current transformers which may be as old as I am. So they have been designed long before the standards have established. They even have not a class definition, so they have other parameters there. So that was a short view into the standardization side. And now we have to look at the steady-state operation. And for that, I will show a simulation. So let's look a bit closer into the steady-state operation. What happens if we have a current transformer in steady-state operation and we run it into saturation? So we come back to this equivalent diagram I already discussed before, and we will now look a little bit more into the behavior of this magnetizing reactance. This is defined by the iron core, and iron unfortunately has a nonlinear behavior, and this behavior can be described by such a curve. This curve shows the voltage across the magnetizing reactance on the vertical axis against the current. That means as long as you have low voltage across the magnetizing reactance, the current is really low. So you see for voltages up to, be careful, this is a logarithmic scale on both axes. So if you have a voltage up to, let me say, 200 volts, you have a current around just 10 milliamps. So it's neglectable, nearly neglectable compared to the currents we want to measure. But then you see this curve becomes flat, and that means a slight additional increase in voltage results in a significant increase in current. And the higher you come, the stronger this behavior becomes. And that means the current through the magnetizing inductance increases significantly. And remember, the current through the magnetizing reductance causes an error because that is the difference between the ideal secondary current and the current our protection relay measures. And I would like to give an example to show how that works. And for an example, we take a current transformer 1500 amp to 1 amp. Primary rated current is 1500 amp. Secondary rated current is 1 amp. And the class of the current transformer is 5P20. You see it's a P-class current transformer, as discussed in the standards before. And this 5P20 means it guarantees a maximum error of plus minus 5%, that is the 5, if the current is up to 20 times nominal current, if you have connected the rated burden, and the rated burden is 15 VA. What we also assume for this current transformer is the winding resistance that is estimated to be 3 ohms. That is a thing you may have to get from the datasheet. And now I would like to calculate the operating point in our diagram for this limit value, for this value of 20 times nominal current. 20 times nominal current means on the primary side we have 20 times 1500 amps, that is 30 kiloamps. And on the secondary side we have 20 times 1 amp, which is 20 amp. And from that we can take our formula in the yellow box, which says that the voltage across the magnetizing reactance is current, 20 amps, multiplied by the sum of these two resistance. Winding resistance is 3 ohms and the burden is 15 ohms. You must be careful at that point. You see, normally the burden is shown in VA as a power. Here we need the value in ohms. If you have a 1 amp CT, it's easy. You can just say the burden in VA has the same number as the burden in ohms. So we take the 15 ohms there. If you have a 5 amp CT, we will see that later on, you have to divide it by 25 to get the correct value. So the result of this computation is we have the 360 volt. And with this 360 volt, we can now go into our diagram. We take the 360 on the vertical axis, go to our curve, and then from there we see the magnetizing current is something between 0.05. So that is the point where we reach the error limit. So you see, saturation, there's not one single point where you can say exactly here saturation starts. It's a gradual thing because the magnetizing current starts gradually. But simplified, we can say up to this point, which is defined by the current transformer class, we can ignore saturation because the current transformer will, according to the standard, operate within its limits. And above that point, saturation starts. So this is the saturation starting point. And I will illustrate this thing a bit more in some simulation I provided for use. In this simulation, I would like to illustrate a little bit what happens if we change some of the quantities around the saturation point we just discussed. This simulation simulates the circuit we just saw, including the magnetizing reactance with this nonlinear characteristic. And what we see here in this diagram is in green the primary or the converted primary current, that means the ideal current we would like to measure. And in red we see the secondary current the connected protection relay gets. And that what we see at the moment on the screen is just the point we discussed a minute ago, where we have the 360 volt and the point where just the saturation starts. You see here the red curve and the green curve are still in line. The only exception is here a starting effect at the beginning. We can ignore that, but later on in a steady state conditions, these curves are identical because we are still within the accuracy limit. And now in this simulation, we have some sliders down here where I can change the short circuit current and also the burden. And if we now increase the short circuit current, you see here we have 20 amps at the moment. And on the bottom, you see the burden is 15 ohms. That means it is exactly that point we calculated on the previous slide. And if we now increase the current, this changes. So I will go up to 40. Oops. And you see if we have 40 amp, that means double current, we run into a saturation error, then we see a complete different picture. You see here in green that what we should measure, and in red that what comes out of the circuit because our magnetizing reactance sometimes draws a lot of current. So you see it typically follows the green curve until we reach saturation point, and then it goes down, and then the same thing is repeated. The pattern you see here depend on some other parameters. So in real life, they may look different, but the basic behind that remains the same. If we increase the current beyond this saturation point, we will have a disturbed curve at the protection relay. Remember, the saturation is defined by the voltage across the magnetizing reactance, which is the product current multiplied with resistance. So I have now increased the current. That increases the voltage, and that drives us into saturation. If we now leave the current at this high value and reduce the burden, then you will see I take the burden back to 6 ohms, and then you see it's fine again. Saturation has gone, because by reducing the burden, we reduce the voltage across the magnetizing reactance, and that reduces the saturation. That means the burden and the short circuit current, that are the two main things who affect where the saturation starts. Now let's go back into saturation. I take the burden back to 15 ohms, where we have significant saturation. Of course, we in protection are not really interested in these curves. They are distorted, it's not nice, but we are interested in protection functions, in that the protection relays work properly. So one question is now, if an overcurrent relay receives such a disturbed curve, what is it going to do with it? What current will it calculate from that? And of course, that depends to a certain degree on the algorithm we use. And to illustrate that, I have just implemented here a simple Fourier filter to calculate the current from this curve. And we can have a look how this looks like. You see here now, additionally in the picture, in dashed lines, what would the algorithm calculate from the green curve? That means from the original nice sine wave. And you see here, after a starting effect, you get stable value, 40 amps, the correct value. The dashed red curve looks a bit different. So you see a lot of ripple on it because Fourier filter is designed for sine wave, and this is not a sine wave. We have a lot of harmonics in it. But the important thing is it results in a lower value. It measures something like 30 amps. That means the current it should measure is 40 amps, and due to saturation, the measurement would be 30 amps. And of course, this effect, we have to keep that in mind, that can cause trouble. And for that reason, it has to be considered and it has to be checked whether that causes trouble. You see, if there is a setting maybe of 20 amps, it doesn't disturb anything, because even that what we measure here, the 30 amps, are still above the setting value. In this case, the relay would trip, and the saturation, this type of saturation, doesn't disturb us. But if we would have a setting, that is not really a realistic case, if we would have a setting of 35 amp, in this case, that would mean the current is 40 amp, the setting is 35 amp, so we would expect a tripping, but that what we calculate from the disturbed curve is only 30 amp, and in this case we would have a missing trip. I would like to show one additional thing in this slide, that is the magnetizing current. Remember, the magnetizing current is that what causes the difference between the ideal current and that what we measure. And in this diagram you see here in blue the magnetizing current. At the beginning of each half period the magnetizing current is nearly zero, and that means the red curve and the green curve are together. And then if we come to this saturation point, then suddenly the magnetizing current increases and the red curve goes down. As I said, this pattern may look different depending on some other parameters, but the effect is always the same. So that was the simulation for steady-state conditions. And I would like to summarize that just in a slide. So this slide summarizes what we saw in the simulation. As long as we are below or on the saturation point, we have nearly no saturation, then the curves look like that. That means the blue, in this case blue, and the yellow curves have identical shape. We measure our protection relay, which is connected to the current transformers, gets more or less exactly the current which is flowing in the line or in the cable. If we increase the current or increase the burden so that we are beyond the saturation point, it looks a bit different. Then we have disturbed current. In this case, we have steady-state saturation. And that means the secondary current, the current the protection relay measures, is distorted, and the distortion comes from the peaks in the magnetizing current. In this case, the shape which came out of the simple simulation using a simple replica, the shape may be a bit different.
Dear audience, if you're interested in more detailed information and practical training, please visit our training platform at Siemens Power Academy. I am confident you will find the right resources and training there. A link to the recording and the slides will be sent to all participants. Thank you for your active participation. I look forward to meeting you soon. Stay safe and take care. Goodbye.